Good morning, everyone, and welcome to day 2 of Google Cloud Next. I hope everyone had a great day at the conference so far. My name is Cheng. I'm a customer engineer in Google Cloud Financial Services. I specialize in application development and infrastructure modernization. Today, I have the distinct pleasure of presenting with my colleagues at Citadel on their migration story to Google Cloud. To agenda set, we'll start off with an introduction to Citadel and the team. Next, we'll cover some finance terms to be cognizant of as it pertains to the workload we are migrating. And then we'll cover the on-premise risk environment and its subsequent migration to Google Cloud, talk through some of the key challenges along the way, and ultimately success from the migration itself. With that, I'll pass it to Sacha to introduce Citadel and the team.
Thank you, Jen, and good morning, everyone. My name is Sacha Best. I'm a senior engineering manager here at Citadel, working in the global fixed income organization. And as Jen mentioned, I'm very pleased to be joined here by 3 colleagues, Aasif, Versi, Cindy Zhang from Citadel, and Jen, thank you for putting this event together, bringing us all here today, and we're excited to speak to you all. So before we get into all the interesting technical bits that I'm sure everyone in the audience is really here to listen to, I want to give a brief introduction as to who Citadel is, what we do, and specifically how Google Cloud fits into this workload that we're going to be describing today. So the Citadel hedge fund is separated into 5 different strategies across credit, commodities, our quantitative arm, GQS, or global quantitative strategies, equities, and fixed income and macro. So everyone on stage here today is from the fixed income and macro organization, and that's the context in which we're going to be discussing the technology and Google Cloud adoption. So I think the first, and I'm chuckling to myself thinking about this, the first question we often get is like, what is fixed income and macro? If you're not familiar with the finance world, like these might be terms that are a little bit foreign or strange. I think when it comes to contrasting the different like asset classes and strategies I just mentioned, the biggest thing to think about is, for those of you who are used to trading equities, you can go on your phone and ask the exchange or ask Schwab or Robinhood or whoever it is, how much is my share of Google worth? In the fixed income world, a lot of what we trade is not traded on an exchange. And that means there's no one to authoritatively tell us how much an asset we hold is worth or how much an asset we might want to get into could be worth. And therein lies most of the technical complexity that we're going to be talking through today. We have a complex series of mathematical models written in mainly C++ and Python that we use to value, measure, and assess risk in our portfolio. And with that, I want to pass it over to my colleague, Aasif.
Thanks, Sacha, for that introduction. So there's 2 main things that we care about in the fixed income business. That's risk and P&L, or profit and loss. So first, let's talk about risk. Risk basically lets us understand how our portfolio is going to react to certain market moves. We want to be able to predict how our portfolio will change due to anything happening in the market. So again, going back to the example that Sacha gave about having a stock of Google in your personal portfolio, you may choose to trade an option on that Google stock. So you may be familiar with something like the options Greeks like delta, gamma, and vega. I'm going to quickly describe delta because that's what we're showing here below, and delta is essentially the sensitivity of your option to a change in the underlying price. So here we show the options delta with respect to a set of futures instruments going out for the next 5 years. So now that we know how much money we're risking, we want to understand how much money we're making, or P&L. P&L is important because like Sacha mentioned, we can't just go to an exchange and ask, hey, what was this OTC or over-the-counter instrument worth? We have a quant research team that is always updating our models to give us the best understanding of our P&L. Because these models are always being updated, we want to make sure that the P&L that we're showing to our traders is up to date as well. So this P&L is bucketed into certain buckets as shown here. So like, I want to know if my P&L went up or down because of inflation or commodity prices or equity prices. There's a bunch of different factors that we care about. These are just a few of them. So like I said, all these models are being updated constantly, so we regenerate our P&L every night And on-prem, this used to take us about 8 hours to do. After moving to Google Cloud, we can do it in under an hour. So this is quite a speed up and makes our lives much easier. So I'll quickly tell you what our computation footprint looked like on-prem. And essentially what it was is we had a fixed worker pool that was shared between all of our users. This meant that if I made a large request, let's say to calculate 1 year of risk, and Cindy makes a request to calculate one week of risk, my large 1 year request could block Cindy's request, and she'll be stuck waiting for who knows how long for her results to come back. So this is like the example of the noisy neighbor problem where I am blocking Cindy's requests. This capacity was also fixed because we had to install servers into our data center. We can't just like borrow servers from Google whenever we want. So that's a little bit of what our on-prem infrastructure looked like.
Thanks, Aasif, for setting the background and walking us through the on-premise risk environment. Next, Cindy will walk us through some of the key design considerations we had as we were migrating to Google Cloud, and also some of the selection criteria for Kubernetes services as we were deciding between GKE, Google Kubernetes Engine, and Cloud Run.
Oh, wrong button. Oopsie. All right, thank you, Jen. So before stepping into the details of our design architecture, we'll first zoom out and talk about the objectives that we're trying to achieve. And as Jim mentioned, a really common question we get is why do we not go with Cloud Run or another vendor product, and why do we choose to build directly from Kubernetes? And one of the reasons is we wanted to embrace the flexibility of natively using Kubernetes. We wanted the ability to quickly tune the different parameters available to us and expose these features to users as we deem necessary. And then on top of that, we wanted to enable a simple user interface, since we're going to be giving this cloud compute infrastructure to people from diverse technical backgrounds, from traders to like QRs to other developers. Next, we wanted users to configure flexible workloads in a MapReduce style. So as the diagram shows, we allow users to pass a sequence of functions that they want to execute in order and a set of initial inputs. These initial inputs can then expand, map, pipe, reduce through all of these different functions until we get the final outputs. Next, we wanted to leverage the resource elasticity that we get very naturally in the cloud. We wanted to increase our horizontal scalability while also decreasing our costs wherever possible. We wanted to also increase resource isolation, since in the previous diagram that Aasif showed, we had one worker pool for every single job. But now that we have elastic resources in the cloud, we're able to spin up a separate worker pool for each job as they come in, essentially solving the noisy neighbor problem from there. And finally, we wanted to create a self-managed and failure-tolerant system. So in contrast to the previous diagram, where the users would connect directly to the system, if the client fails, that was it. You had to retry your entire job. But now we can have a failure management system within the cloud itself. Okay, so diving deeper into the design architecture, as the diagram shows, in order to accomplish our objectives, we use several different Google products. We use Google Kubernetes Engine, PubSub, Google Cloud Storage, and Bigtable. So to walk in more detail for the design, I'll walk you through the lifecycle of a job. So at the very beginning of the diagram, we have the connection between the user and the server. Here is our simple Python interface, and that will encapsulate the complexity from the rest of the system. In this Python interface, the users will submit what's called a job spec whenever they want to start a job. Within the job spec, they have parameters such as the number of workers that they want to allocate to their workload, the CPU memory per worker, the Docker environment that the workers want to run in, as well as the set of functions they want to run and initial inputs. So those are the basics, but we can also leverage the rest of the complexity of the system and expose tunable parameters to users who want to run more complex workload, more like specific workloads from there. So as the server receives the request to start a job, it will launch a separate GKE deployment called the job manager. So as the job manager, the name suggests, it will manage the lifecycle of a job. Here it also has internal retries for transient failures and also consistent failure modes. One thing that's noteworthy is that the job manager onwards, so the job manager, the pub subtopics, and the worker pool itself, these resources are ephemeral. They're created whenever a job is launched, and then they're torn down whenever the job terminates. And we have consistent failure modes so that whether or not the job is successful, the user code has errored out, or even if there is an infrastructure failure, we make sure that the resources are cleaned up. And at the end of the job manager will also delete itself. So from there, to pass messages between the workers and the job manager will send all the tasks and inputs through one of the pub subtopics. The workers will work on these tasks and send them back through the other pub subtopic. And this cycle will repeat until the entire workload is done. And at the bottom here, we show a persistent data layer. This is helpful for multiple reasons. One of them is to pass larger messages between the job manager and the worker pool. If the data is small enough to be serialized and passed inside of the pub sub proto, we'll do that. But oftentimes this is not the case. So we have tuned our storage so that medium-sized inputs can go into Bigtable, but larger ones will go into Google Cloud Storage. And from there, we can pass the storage key in the pub sub proto instead. And since this data layer is persistent, it also not only stores the initial inputs and the final outputs, but also all the intermediates. This means that when a job fails, we can consistently replay failures or even replay part of the job that failed. And also, the user is now able to submit a job and then long after the job completes, retrieve the results asynchronously.
With this design, Cindy, could you talk us through some of the key scenarios that we enable for end users? And also, what are the challenges that are unique to each one of these scenarios as well?
Sounds good. So to start, our cloud compute workload can tackle two seemingly divergent workloads. The first one is the high fan-out case that we have been discussing so far. This is a case where we will request thousands of workers at a time and spin them up and down as necessary. So some examples of this use case would be regenerating year-to-date P&L, like Aasif has mentioned earlier, or just computing the long history simulated performance of searching portfolios. And here we have isolated worker pools to solve for the noisy neighbor problem. And then on the other hand, with just a few tweaks to our infrastructure design, we can support real-time use cases. So the real-time use cases we're talking about are requests that return in a matter of seconds. So these are going to be the ones that generate live results that power interactive user interfaces. Some use cases include computing the hypothetical performance of a specific trade. So the user, a trader, can submit a hypothetical trade that they haven't placed and then see how this trade would impact their existing portfolio without ever taking on the risk of placing that trade. And another use case is to display the computed historical pricing of a specific instrument, since our fixed income instruments can't just be looked up in exchange for the price. And in the real-time case here, we actually have a persistent worker pool that is set up throughout the day to receive these requests and execute them. And the difference between this real-time worker pool and the shared worker pool we saw earlier in our previous on-prem design is that this worker pool can auto-scale based on usage. Next, I'll walk you through some of the challenges that we face in the cloud, as well as the solutions that we came up with while working with Google. The first challenge is GKE scaling. So our workloads are pretty inconsistent and also highly varied, since a lot of them are user-triggered. We have some workloads that run for many hours on end with just a few pods, but we also have workloads that run for maybe 1 hour with lots and lots of workers. So whenever we schedule a job that is wide, it causes a lot of pod shuffling, and it makes the long-running workloads unstable. So the solution we came up with was, instead of requesting just the number of workers that we wanted to schedule from Kubernetes, we could tightly pack containers into pods and pods into nodes so that we can request specific instance types and a specific replica count for that instance. Now that the nodes are optimally packed with respect to CPU and memory resource utilization, when we schedule workloads of varying sizes, we no longer have to deal with arbitrary pod eviction and rebalancing in the cloud. And as an added benefit, now that we can deterministically request the specific nodes that we want, we can now consistently compute the cost for every single job that we schedule. Another problem related to GKE scaling was for the real-time workloads. These are also user-triggered, so it is kind of inconsistent and spotty throughout the day, and therefore it becomes not cost-efficient to pre-allocate a static set of resources, because we don't know if we're going to get the maximum load throughout the entire day. The solution for that was to use horizontal pod autoscaler, and we'll autoscale based on pub/sub's number of unacked messages, aka queue depth. And this way, we can responsibly scale to user requests as they come in throughout the day. A related challenge is the classic cold start problem. So resources in the cloud that are elastic, like pub/sub and GKE nodes, they take time to scale up, and they also cool down quickly. As the graph shows, it is the end-to-end latency of a specific pricing request, and on the x-axis, we show the number of minutes that the system remains idle for. As you can see, even if the system sits idle for 5 minutes, the next request that comes in is essentially a cold start. And since the real-time workloads are being user-triggered throughout the day, and it is spotty and unpredictable at when they will come in, we run the risk that every single user is going to encounter a cold request. So the solution for that, to keep pub/sub warm, we will consistently send it heartbeat messages so that the system will register throughput and not scale down as quickly. To let GKE nodes spin up faster, we also create low priority pods in GKE, and these can have images pre-pulled onto them. And since they're low priority, when a real workload comes in, these pods can be quickly evicted and their resources can be surrendered to use on the real workloads. Okay, so now that I have walked you through some of the objectives and our design, as well as the challenges and solutions that we came up with, I'll pass it back to Aasif to talk about some of our successes today, and Sacha to talk about what's coming in the future.
Cool, thank you. So with this new design that Cindy just walked us through, we have much faster end-to-end job request times. Our users are getting their results faster. We have flexible and scalable compute that can be configured directly by our users. Our resources are now isolated, so we no longer have the noisy neighbor problem. And we are able to leverage the cloud for new real-time workloads, one of which I'm going to walk you through. So one of the new tools that we were able to create is this backtesting on-demand UI. So this is essentially a UI that's available to our traders where they can just type in a hypothetical trade idea and quickly get their results back. So a trader may want to perform a hypothetical trade to understand how this trade will impact their portfolio as a whole, especially when looking at historical scenarios like the financial crisis in 2008 or COVID in 2020. So here we have an example of buying an S&P 500 call option that expires in 2010, pretending that we started in 2009. So on the pink line, you can see the strike price of the option, $1,000, and the index price in the orange line changing over time. The green line is the value of our option at start and all the way to the end. And what you can see is, like I described earlier about the delta is changing over time as we get closer to expiry. And at the end, we have a delta of 1, which essentially means that as the index price goes up, our option price will also go up by that same value, basically because we're in the money and the index price is over the strike price of the option. So this is kind of a straightforward example of buying an equity option, an equity index option, but a trader could put any hypothetical trade they want, even including those over-the-counter trades that we were talking about earlier. So now I'm going to pass it back to Sacha to tell us about what's next.
Thanks, Aasif. So I very much appreciate, Aasif and Cindy, the technical detail you just went into about all the systems we built in conjunction with the Google Cloud folks in the room, and grateful for all the support therein. I think it's interesting to think about now that we have these kind of archetypes or fundamental primitives for both batch job runs and real-time use cases, where do we go from here? As the general question and what we're thinking about there is, as Aasif just went through, we are no longer constrained by technical or infrastructural challenges when it comes to testing, trialing, or doing research on what our portfolio might look like. We're now only effectively constrained by our imagination and creativity of our investment professionals, researchers, and engineers like ourselves. It's a very fun place to be because we can spin up new workloads and kind of trial things at will with high business value for effectively very low incremental cost over what we've already incurred and effectively built up. So one interesting use case, again, from the same UI Aasif just mentioned that we have on the screen is showing, I believe, the linear regression between two trades on the left, and then on the right, the residuals of that regression. So to kind of go from a finance world to more of an ML, AI world that might resonate more with the folks here in the room, this linear regression is pretty naive. You can imagine there are various different regression types you could use to measure similarity or other correlations between two series. You could imagine doing the same analysis with L1 or L2 regularization, so on and so forth. All of that is now effectively possible because it's just effectively plug and play a different mathematical algorithm into a system that already exists. The other thing I want to mention is that the risk system Aasif and Cindy just described that started in fixed income is going to become Citadel's risk system. I think that is really demonstrating and effectively speaking to the power and fidelity that we get from Google Cloud in the sense that we can optimize and effectively refit this system that's very tuned for the mathematical intricacies of fixed income to all the other asset classes we talked about, credit, commodities, and equities. With that, I want to pass it back to Jen for a closing.
Cool. Thanks, Sacha and team, for sharing your story with the audience today. Some closing thoughts or takeaways are the following. The worker queue pattern we described today, this is applicable beyond risk computation and financial services. This works well for any workloads that might have a large influx of incoming work that may require some amount of queuing. Furthermore, the worker nodes themselves could be replaced with other GCP services, such as Compute Engine, Cloud Run, or Cloud Functions. It really depends on your level of familiarity with each one of these services, the amount of flexibility you're looking for, and also management overhead.